so now we're going to kind of add into our advection dispersion equation, which we've been doing. We're going to add in reactions, transformations, sorption, all those fun things that decrease the concentration with the contaminant. Advection and dispersion tells you that if there was no reaction that occurred, no transformation, nothing occurred to the system, no sorption, no retardation at all, this is what would happen. So we're going to be looking at the advection with things. So if we're going to look at that change in the concentration with time, we know this part is the dispersion part. We've looked at that quite a few times. This is our advection part of the equation. And now what we're going to do is decrease the concentration by absorption. And then we're going to add to it reactions, which is going to change with time. So this right here, these two added together, is the reaction and the absorptions, and this reaction can be biological, it can be chemical into there, and these two added together will decrease from these from the dispersion and absorption to change the concentration with time. So we're going to be looking at retardation, or we call this R in there, and this is a combination of absorption, which we've already kind of discussed, biodegradation, decay, precipitation, like if something precipitates out, so if it comes out of solution. I use PPT for that, okay, just so you know. Redox reactions, etc. So we're going to spend some time talking about all these different forms that cause the retardation of a compound. So these are all different types of transformation processes. So some of these things are like precipitation and dissolution. So like if we have precipitation and dissolution. So contaminated groundwater is often not in equilibrium with the minerals and of the soil. Okay, so as there is water coming into the system, so say if you have like a BTEX compound inside of into the air, or you got a VOC inside of it, it might not be in equilibrium with your soil. So as the water equilibrates, sometimes it's hard for me to say, with the minerals, it may dissolve or it might precipitate out, and there may be an ionic contaminants can be removed by precipitating onto a solid. Okay, so examples of this is like if you have a mine tailing, you have dissolved oxygen in the rain. So let's give you an example of this. So here's an example. So say we have like a dam here, we've got groundwaters here, we've got a dam here, we've got some mine tailings. They're piled up here, and so the contaminants are coming underneath the dam inside of here. This is our symbol for groundwater. So, and then we have rain coming in this way. The dissolved oxygen in the rain reacts with the sulfide minerals in here. So we have the O2 in here reacting with the sulfide minerals in here. So the sulfide minerals inside of the mine tailings. And this lowers the pH, so we decrease the pH of the solution because of that. This is acid mine drainage. It lowers the pH. Well, that lowers the pH. What happens when you lower pH, and we'll get more into like pKa's, what happens is when you lower the pH down, you release the heavy metals. So this happens like anything that's less than a pH less than 2, you're going to be releasing a lot of heavy metals. So what's happening is this oxygen going into here, coming out here, and now we're going to be releasing things like iron, copper, lead, zinc, mercury. All these wonderful metals get released. So what is happening is we're having precipitation coming in here, causing this reaction to occur. Now all of a sudden we're getting contaminants of heavy metals downstream from there. If there is a sufficient carbonate mineral in the soil, the acid could be neutralized. So say we had a vein in here in the dam where we put in calcium carbonate. If we put calcium carbonate in there, that could cause, or even downstream. So say we put in a reactive bed like a curtain in here. So we dig out a trench, and so as the groundwater is going through this, this is filled with limestone. Inside of there, crushed limestone, and as the groundwater is going through this reactive curtain, what will happen is this will raise up the pH, and all of the heavy metals will precipitate out. And then they'll be left inside of this area here, and then coming out, you could remove the clean groundwater. If there's no carbonates in the area, the pH remains low, and the toxic metals can migrate substantial distances. And and this could eventually, without this curtain here, or without any sort of reaction, this could eventually get into streams, rivers, kill fish, and stuff like that. So this could be an example of how rainwater and understanding the geochemistry of the system can release a contaminant that really wasn't in here at all. Well, it is in here, but it's like in the solid phase here, and then becoming into the liquid or into the water phase down here. Our next system that we're going to talk about is radioactive decay. So this is decay. This is not our stable isotopes. This is our radiogenic. Decay of unstable isotopes causes irreversible loss of the mass of that isotope in the system, but does not retard the transport. Okay, so it doesn't change the transport of the contaminant you're looking at, but it will decrease the concentration with time. Can produce hazardous daughter products or byproducts. We used to call them daughter products. We're trying to change that, so more of reactants or products. So, like an example here of this is tritium going to helium plus a beta emission. So it's giving off radioactive decay. So how would you think that the breakthrough curve would look? So we're going to look at the breakthrough curve here. So if we had a breakthrough curve, this is our time, this is our C over C naught. Well, what would happen is, our normal breakthrough curve goes up and comes back down. Now, what would the breakthrough curve look like if we have something that is decaying relatively quickly and stuff like that? And it transports the same. Let's say it's hydrogen of some sort, which is, so this right here would be a non-decaying, no sorption, solute. So, example of this is the chloride that we've been talking about. Well, what would happen if, say, it did the tritium? Well, it's non-sorbing. It's completely soluble in water. So what would the breakthrough curve look like? Okay, so what do you guys think? So we know that it's going to come through, the main part of the mass is going to come through at this time. So would it reach this high level? Because this is our 1, this is our 0. Would it go all the way up to the top here? No, because we've lost mass, so it can never reach the original concentration that we put in. So we're going to get some less mass that comes in here. And since it's decreasing, we may not see it for a little while, and then it'll go away faster. And so something like tritium would be like this, where it moves just like our chloride, but it's decreasing in the amount of concentration, and it shows up later because it's starting to go away in there. So we have the same breakthrough curve, but we have a decrease inside of here. But this magical time when the highest point here, that would remain the same with advection. So radioactive decay is one type of way of transformation process and how we would look at it through the system. Another one that we can look at here is microbial degradation. So this is microorganisms. So this is our bacteria that are found in our soil systems. They will break down the compounds, some of them. And we talked about aerobic versus anaerobic. We talked about this a little before. So say we have BTEX. plus microorganisms. I use MO for microorganisms or BT for bacteria. That's what I use. Plus, now you have to have the right nutrients in the system, the oxygen levels, etc. So a correct thing. You will go to CO2 plus H2O, and this is mineralization. So it completely breaks down the BTEX compounds into CO2 and water. That is a mineralization into there. You could also get some example of this like nitrate into a system, plus bacteria, plus organic carbon. So you need some carbon into the system. You're going to get N2 gas plus CO2. Okay. So these processes are irreversible. So once these BTEX compounds go into CO2 and water, well, okay, so in order to go back to the BTEX compounds, the CO2 has to be taken in by a plant. That plant then needs to be buried into the ocean, buried under anaerobic conditions, sit and maturate, and then you can go back to your BTEX compounds. We're talking millions of years to go back to this. Well, it's very quickly to take the BTEX compounds and mineralize them. Same thing with nitrates. In order to create nitrates, there's a whole bunch of chemical processes that go into it. There are certain microorganisms that can take nitrogen gas, nitrogen fixers, and these are usually found in like beans and stuff. Lightning strikes can do this too. Can change it back into bioavailable nitrogen compounds, but generally these things are irreversible. And these things, unlike radioactive decay, which is, we know exactly how fast this happens. I mean, you could look this up. You know the tritium. I don't know the half-life of tritium. Let's look that up real quick. Hold on 1 second. It's 12.32 years, so I couldn't remember that one off the top of my head. And so we know exactly how fast this rate of decay is for radioactive isotopes. But when it comes to microbial organisms, there is so much that's inside of these black boxes, systems. It really depends on the microorganisms that are in there. We can come up with estimates, and you can find these things for what, and we use the same type of thing. We use the thing called a half-life, too, for microbial biodegradation. So we use the half-life idea for both of these. So let's look at half-lives. So half-life. This is T equals 1/2. So this is the time for N, so, or whatever it is, to decay to half of its initial value. So if this is a concentration or half of the number of atoms or whatever you have here, the mass, number of moles, whatever it is, this is to get to half of that. So for the equations for stuff like this, so to put into the advection dispersion equation, we can look at N equals N naught. So our original starting concentration is e to the negative lambda t, where so this is the equation for half-life. So if we assume that N equals 1/2 NO, and then we substitute that into this equation, so we go NO over 2 equals NO equals e to the negative lambda t to the 1/2. Then t equals t to the 1/2. We get the natural log 1/2 equals negative lambda t to the 1/2, or the time of the half-life equals 0.693 divided by lambda is our main equation here. Okay, and so a lot of times you can look these things up. You know, lambda is just a rate constant that we look at, and so we can have nucleotides. Examples in the time to the 1/2. Can't draw that one in years. We just looked up tritium because I couldn't remember it. Was 12.32 years. Okay, carbon 14 is 5 times 10 to the 3. Strontium 90 is 29 years. Uranium 235 is 7 times 10 to the 8th years. So you can use these things and these models to fit in these others. Now, this idea of half-life, when we look at these radionuclides, these are very defined. Like I said, for microorganisms and for other chemicals, these things are not as defined. And so we have to come up with experiments in order to determine this. And so what we do with those is we do what are called batch experiments. Batch experiments. So a batch experiment is like it kind of sounds. You take a vial, we close it up, or we put in gas or whatever it is. We add some soil into here. We've got water into here, and then we add the chemical that we're interested in. So the soil and the water from the site has the microorganisms into there. We add the chemical, whatever biological chemical is in here. We shake it up, and then we monitor it with time, and then we see how long it takes. So we monitor it, and we take the natural log of the concentration over time, and we get a straight line inside of here. And so what we do is from this equation here, from looking at the natural log of the concentration with time, we get a straight line, and then that will give us our half-life inside of here. So we can determine our, we know our CO, and then we can determine our lambda from this, and then we can determine getting our half-lives and everything like that. So we get our rate constant from this. So what we're going to be looking at is the advection dispersion equation with first order decay. So this is what we're talking about. These are first order type decay products, especially with half-lives inside of there. So we have the change in concentration with change in time equals our dispersion. You guys should recognize this, plus our velocity. We already talked about this. Plus our change in their concentration with our change in time reaction. So inside of here. And so the rate equation equals the concentration at time equals our C naught E exponential to the rate of time. And so what we assume is that concentration equals concentration at time over C naught equals E T. And so if we assume these things, we can say the change in time equals, we can derive these things, equals e to the negative. So it equals negative lambda C. So that's basically it. So first order decay is really easy to add to the equation, because once we know the rate constant, we know what the concentration was, then we know how fast it's decaying inside of our system and stuff like that. So, and again, going back to our breakthrough curves. So say we have our breakthrough curves here. We can use time or we can use distance. It doesn't really matter. We've got our C, we've got our C naught, our concentration of 1 up here, and we've got our C over C naught. We've got our standard one that reaches our concentration of 1 here. And stuff like that. So this would have a retardation factor of 1 inside of here if the lambda equals 0. So there's no decay. No decay. Now, if we have something with decay, remember this one comes through at the same time, so this is the R equals 1, but our lambda is greater than 0 because there is decay. So this different distance here between here and here also helps us to determine our concentration inside of there. Now, let's say if we have a retardation factor of 2, if it has no decay, but it has a retardation factor of 2, where would that look like in here? Well, what it would do is it would come through later. So this is distance. Let's call this time. Let's use this one as distance down the well. What it would do is it wouldn't move as far. wouldn't move as far as that one. So if we have an r equal to 2 and our lambda equals 0, it wouldn't move as far because we have that retardation, so it's being decayed, so it's not coming as far as this one did because it's being retarded inside of the system. It's also the underlying of the system, because there is no transformation of it, is exactly the same, except for, I can't draw very well, it would be much more overlapped. Then if we had something with a retardation factor of 2, it would come through here, especially if the retardation equals 2 and the greater than 0. So it would be decreasing down in here too. So what it would do is, if we have retardation in the system, it's going to move it back, and if we have it decay, it's going to move it down, because that is getting rid of the concentration inside of the system.